Assalamu alaikum everyone. In today's video lecture, we learn about non-aqueous acid-base titration under the course of pharmaceutical analysis. So let's start. So the principle is the organic acids and base are insoluble in water. These are extremely weak and cannot be analyzed using normal tritymetric method. Hence, the non-aqueous tritymetric methods are employed. Usually, most of the drugs are either organic acid or bases. Actually, our drugs are not strong acid or strong base, as most of the drug are weak acid or weak base. That is why non-aqueous acid base titration is performed for them, for the determination or the measurement of the drug, or for analyzing the assay. The main principle involved in the non-aqueous tritymetric methods is the samples are dissolved in non-aqueous solvent. So hence the name is non-aqueous, because in case of aqueous solvent used uh, we usually performed our acid base titration, that is utilizing some HCl or sodium hydroxide, etc. But in case of non-aqueous titration, we usually employ uh, weak acid or weak base. Okay. So to understand the rationale or application or the significance of non-aqueous titration, we need to analyze the differences between aqueous and non-aqueous titration. Usually in case of aqueous titration, we use water as solvent. Okay, but in case of non-aqueous titration, we usually use glacial acetic acid, DMF, etc. Then it is used for strong acid and strong bases, but non-aqueous titration is used for weak acid and weak bases, as most of our drugs or pharmaceuticals are weak acid or weak base. So this is the most commonly used techniques for determining or the measuring or potency analysis of our pharmaceutical products. For example, HCl, sodium hydroxide, H2SO4. Then in case of non-aqueous titration, we usually analyze the measurement of ephedrine, barbiturates, etc. Then endpoint clarity, it's good for a strong acid or base, and obviously it's sharp for weak drugs, that is weak acid or weak base. Then pharmaceutical use, it's used for it's limited for raw materials only, and it is widely used for drug assay. So this is the basic rationale for using non-aqueous titration. I think you have already found a idea about the non-aqueous titration and its significance and rationale behind the scenario. So why non-aqueous titration? They are employed due to the three vital problems of quality control, both in pure and dosage form, by virtue of their inherent characteristics. Namely, reactants are insoluble in water or poor solubility, and reactants are weak reactive in aqueous medium, then reactants are very weak acidic or very basic in nature. Okay. Initially, the above three problems are usually avoided in the following manner, like amine salts, sodium salts, and nitrogen containing compounds. Usually the problem that has arisen that our most of the compounds are weak acid or weak base. We have minimized this problem by utilizing the amine salts of the drug, or sodium salts of the drug, or nitrogen content compound, because these enhance the solubility of the overall compounds or the drugs. Okay, but you know these are not so much effective. Okay, so in case of amine salts, is the fast change to the water soluble free bases extracted with an appropriate organic solvent and treated with excess amount of standard acid subsequently. The solvent was evaporated and the remaining acid determined with the standard base. Then sodium salt, it is first acidified to release the water insoluble organic acid extracted with suitable organic solvent, and solvent was removed and the residues was subsequently dried and weighed. Then nitrogen containing compounds, they are estimated by micro Zelda method. Nevertheless, such specific quantitative method gave rise to certain serious anomalies and drawbacks. So let's discuss different advantages of non-aqueous titration. Elimination of poor solubility of organic acid and bases that are insoluble in water, then enhancement of weak reactivity of substances, then selective titration by using suitable solvent, and treatment of acidic or basic components of physiologically active moiety of the salt with base which have Kb values less than 10 to the minus 6 can be titrated by using non-aqueous titration. So what is the basic theory or principle of this non-aqueous titration? According to Bronsted-Lowry theory, the various reactions that takes place during many non-aqueous titrations, where an acid is a proton donor and a base is proton acceptor. Therefore, when an acid undergoes dissociation, it gives rise to a proton and the conjugated base of the acid. So according to the Bronsted-Lowry theory, usually water is not used as doses of Arrhenius method in case proton is removed from an acid. Okay, then conjugate acid and base is formed. Okay, now we'll discuss different solvents which are used for non-aqueous titration. So actually there are four types of solvent which are used during pharmaceutical analysis. One is protophilic solvent, then protogenic solvent, then amphiprotic solvent, and aprotic solvent. So protophilic, so proto means proton and philic means uh, favorite. So these solvents uh, like proton, that means these are basic solvents, nothing else. Then protogenic solvent, they can generate proton, that means these are acidic solvents. Then amphiprotic solvent, these are both acidic and basic. And aprotic solvent, this is neither acidic nor basic. Okay, aprotic, A means something absent. Okay, so no proton. So they can be of two types, like polar aprotic solvent and non-polar aprotic solvents. First of all, protophilic solvents. The word proto means proton and philic means loving. The solvent which accept proton is called as protophilic solvent. They are essentially basic in nature and normally react with acid to form solvated protons. For example, liquid ammonia, sodium hydroxide, potassium hydroxide, ammonium hydroxide. So effect of protophilic solvents on the properties of acid base. We'll discuss this leveling effect and differentiating effect one by one. First of all, what is leveling effect? So these two effects are very necessary regarding our protophilic solvents. As the name suggests, level means something leveled. Okay, something similar thing, or some solvents are in same level, that is in the same floor. Okay, so we have to treat them equally. It means something like that. So in leveling solvents, several acids are completely dissociates and having the same strength. Okay, for example, you're using hydrochloric acid, hydrofluoric acid, sulfuric acid, hydrogen iodide, all are having the same result. So weak acids are normally used in the presence of strongly protophilic solvents, as their acidic strength are then enhanced and then become comparable to those of strong acids. This is known as the leveling effect. In other words, strong protophilic solvents convert weak acid to strong acid is known as leveling effect. Okay. Generally, strong bases are acted as a leveling solvent for strong acid as well as weak acid. Okay, you can easily understand this if you follow this table. So look at this table. We have hydrogen iodide, hydrogen bromide, hydrochloric acid, nitric acid, sulfuric acid. So they have been arranged based on their strength, because uh, hydroiodic acid is the most is the strongest acid, which has a pK value less than 10. That means the lower the pK value, the more strong would be the acid. Okay, then SBrHCl. So in theoretically, these are highly acidic, then these are weak acid. Okay, upon descending from the top to bottom. Actually, this is the basic theory. But whenever water is used along with them and for their ionization, what happens? In presence of water, they are 100% ionized. All of them are 100% ionized, although they are having different strengths, or they are having different power. Okay, that means water level these 5 acids. Water has not differentiated these 5 acids. Rather, in presence of water, all of them are having the same strength or are having the same ionization. So we only see the result. As these all are having the same results, then obviously we can say that water is having some leveling effect among these 5 acids. So that is the leveling effect. Now we'll talk about differentiating effect. So it is as opposite to the leveling effect. In leveling effect, all of them was same, but in differentiating effect, as the name suggests, all of the acids strength would be different. So in differentiating solvents, several acids are dissociated to different degrees and having different strength. Okay, generally weak bases are exact as differentiating solvent for strong acid as well as weak acid. For example, H2O is acts as differentiating solvent for hydrofluoric acid, and usually glacial acetic acid are commonly used for differentiating. For example, you have HCl4, SBr, okay, HCl, HNO3, okay, all of them are somehow very much similar in case of their pKa value. They are much more similar, but whenever we are using glacial acetic acid for their ionization, we can see that HCl4 is having 100% ionization, SBr is having 90%, hydrochloric acid is having 70%, nitric acid is having 50%. So you can see that ionization is different for different acids. So we can say this is a strongest acid, this is the moderate acid, this is a weak acid. So we have differentiate their strength. So this is the visual phenomena, and that means the differentiate effect. So water is using as leveling effect, and glacial acetic acid is used for differentiating effect. So if you have further confusion, you can look at this table, because this table differentiates leveling and differentiating effect. Okay, so makes all acid or base appear equally strong, and it preserves difference between acid or base. So solvent type is water, and here we see glacial acetic acid. Okay, for acid level all acid, for base level all base, but its task is to differentiate. And result, all strong acid become proton or hydronium ion, because all will have the same result. And its result is strong acid ionize more than the weaker one, because in presence of glacial acetic acid, this differentiation is generated. So can you distinguish? Obviously, by differentiating effect we can differentiate, yes, but by leveling effect we cannot differentiate. Now our protophilic solvent has been finished. Now it's time for our protogenic solvent. The word proto means proton and genic means genet. Obviously this means some acidic solvent, okay, like anhydrous acid, like hydrofluoric acid, sulfuric acid, hydrochloric acid, etc. These are protogenic solvents. Then amphiprotic solvent, they possess both protophilic and protogenic characteristics. These types of solvents able to donate proton as well as accept proton. For example, acetic acid, water, and alcohol, they undergoes dissociation to a very less extent. Acetic acid is mostly employed as a solvent for the titration of basic substance, and its dissociation can be depicted as shown below. And lastly, aprotic solvent. These types of solvent neither donates proton nor accept protons. Aprotic solvent include those substances which may be considered chemically neutral and virtually unreactive or inert. These may be fall into two types, like polar aprotic solvents and non-polar aprotic solvents. So polar aprotic solvents are acetone, DMSO, okay, dimethyl sulfoxamide. Then non-polar aprotic solvents are benzene, toluene, hydrocarbon. Aprotic solvents are frequently used to dilute reaction mixtures. Then we'll discuss about the methodology. For non-aqueous titration, the following 4 steps are usually taken into consideration, like preparation of 0.1 normal perchloric acid, standardization of the perchloric acid, then choice of the indicator, and the effect of temperature on assay. So the overall preparation of perchloric acid has been shown here, because this is required. Okay, you need to perform some titration. Okay, so this is your perchloric acid, this is your glacial acetic acid. Okay, then you will start and make the volume up to 1 liter. Okay, then you will take potassium hydrogen thalate, then 25 ml of glacial acetic acid will be added to this, then 1 until the salt gets dissolved, then cool and titrate with 0.1 normal perchloric acid, then observe the endpoint. So by observing the endpoint, you can easily determine your weak acid or weak base, or its concentration, or its amount, or its volume, whatever it is. Okay, this is a usual titration that we have already performed in aqueous acid base titration. Okay, so assay by non-aqueous titration. So non-aqueous titration can be categorized acidimetry and alkalimetry. So in acidimetry, usually alkali drug is used. In alkalimetry, usually acidic drug is used. So where from the name comes from. Okay, where does the name comes from? Actually, acidimetry comes from the titrant. In this case, acidic titrant is used. Okay, so acidic titrant will be used for basic drug, and for alkalimetry, usually alkaline solution is used. Alkaline titrant is used. Okay, so alkaline titrant would be used for acidic drug like barbiturates. Okay. So here is the step-by-step procedure for titration. First of all, I will give you the sample. You have to weight this. Then you have to dissolve this in glacial acetic acid, because this is the most commonly used solvent for non-aqueous acid-based titration. Then add few drop of crystal violet indicator, because this is necessary for endpoint determination. Then titrate this with perchloric acid. No, usually perchloric acid for this. Then watch color change. Okay, this determines the endpoint. Then note the volume of the perchloric acid. So the volume of the perchloric acid will ultimately determine the sample. Okay. So acidimetry non-aqueous titration. It is useful for the quantitative estimation of basic drug. I have already said this. That means in titrant would be acidic perchloric acid. Solvents would be glacial acetic acid. Indicator would be crystal violet. And its application would be for basic drugs like morphine, ephedrine, adrenaline, acyclovir, caffeine. Okay. In alkalimetry, it is just opposite to that of acidimetry. So in that case, nalidixic acid, okay, acetazolamide, allopurinol, mercaptopurine, this drug would be used. Then let's check the advantages. So non-aqueous titration have following advantages, like it can be used for weak acid or weak base. Okay. Analysis of acid mixture. Then it can produce precise results with sharp endpoints. It is simple and straightforward. Then extremely important pharmaceutical product analysis. Then having a high degree of selectivity. Okay, can be used in the analysis of tetracycline and histamines, codeine phosphate, and many others. So common pharmaceutical drugs which can be analyzed by non-aqueous acid-based titration has been shown here. So acidic drugs, this can also be analyzed by non-aqueous acid-based titration. However, there are some disadvantages of non-aqueous titration, like when compared to aqueous solvent, non-aqueous solvents are less stable. Then temperature correction are required from time to time in non-aqueous titration. Then calibration is required after each and every use. So this is the overall lecture from non-aqueous acid-based titration. If you have still any confusion, please inform me in the comment section. Thank you.